to another video, guys. Today we will be launching a rocket as well as using math and physics to find the height our rocket will achieve. And then we will prove this height using a little homemade handy tool that I will explain later in the video. So let's get started. The first thing we're going to do is the most boring part, I guess you could say, is the math. We're going to use some physics, some simple physics, to find out how high our rocket will go. So the equations I'm going to be using today, I will attach a PDF of them down below, so you can always come back to them later if you need them. So first things first, we are going to be using Newton's force equation, which is force is equal to mass times acceleration. I should say the sum of the forces is equal to mass times acceleration. So the sum of the forces is all the forces added together is equal to the mass of the object multiplied by the acceleration of the object. So in this case, we're not going to be using air resistance because like I explained in the previous video, it is a pain in the booty. So we are going to be using just force of thrust and force of gravity. But as we write this equation, the sum of the forces is equal to the force of thrust plus force of gravity. But we quickly see that the force of gravity is not in the same direction as the force of thrust. So what we're going to label is the upward direction is going to be positive, because as you go up in elevation, it's going to be up in altitude. You're going to be increasing in altitude, and we're going to put the downward direction as negative. So because the force of gravity is going down, it is a negative force. So we're going to put a negative sign in front of that force. And as we know that plus minus a negative is just minus, so we can get rid of that plus and put it like that. So this is our initial equation, our first equation. The sum of the forces is equal to the force of thrust minus the force of gravity. Like I said before, air resistance, because we are not using it, our altitude will be off by probably around 50 meters-ish, I want to say. I don't know exactly, because it is different for each rocket and for each engine, because we will get into that in a later video because it is such a pain. Anyway. So as we said before, the sum of the forces is equal to the mass of the rocket in this case, multiplied by the acceleration of the rocket. So we're going to substitute that in. So mass of the rocket multiplied by the acceleration of the rocket is equal to the force of thrust, which we could also substitute for the mass of the rocket multiplied by the acceleration of thrust. Because the mass of the thrust there's no mass of thrust. So it's just the mass of the rocket. But the reason why we're not substituting it is because online they only give it to us in force of newtons, which is force because force is measured in newtons. So we are not going to change it into this. We're just going to keep it as mass of thrust. But because force of gravity is given to us in acceleration, we can substitute that. So again, force of thrust is given to us in newtons, which is what force here is measured in. So we're going to leave it like that for now. But force of gravity, we are given it in mass times acceleration. So we're going to substitute force of gravity, but not force of thrust. Please ask in the comment section below if you have any questions or are confused by anything, and I will try to clarify it up. So force of gravity is the mass of the rocket times the acceleration of gravity, which is also written as just g. But here we're going to put A of g, acceleration of gravity. So our next step here is trying to get acceleration all by itself, the acceleration of the rocket all by itself, because we will then use that acceleration to plug into another equation to get our speed of the rocket and then after our height of our rocket. So we are going to divide by the mass of the rocket so we are left alone with just the acceleration of the rocket. So we divide everything by mass of the rocket, which those two will cancel out. And as you can see here, force of thrust divided by the mass of the rocket is also the same as acceleration of thrust. So we're technically solving for acceleration of thrust without having the acceleration of thrust as a solid number, if that makes sense. So we can rewrite this as acceleration of the rocket is equal to force of thrust over the mass of the rocket minus, and like I said earlier, acceleration of gravity is also written as g, so I'm going to put a g in there. And that is our acceleration of the rocket. That is the equation we're given. later on when we solve, well, I guess we could do it now actually. So let's get the number or the acceleration value of our rocket. So the force of thrust of the rocket is 4.7 newtons. As I said earlier, we are only given the force in newtons over the mass of the rocket. So I'm going to have two numbers. I'm going to have the mass of the actual rocket itself plus the mass of the engine, because the engine is being put inside the rocket. So the mass of the rocket plus the engine. The engine weighs 24 grams, but for physics we need to put it into kilograms, so we put it like that. And then the mass of the rocket is 0.09 kilograms, or 90 grams, minus our gravitational constant, our acceleration of gravity, which is 9.81 meters per second squared, or meters per second. So after we do all the math for this, we will be given our value for the acceleration of the rocket, which is equal to 4.7 newtons over, if we add that up, we get 0.114 kilograms, I believe. We had 24 plus 90, 114. Yes. Minus 9.81 meters per second squared. Now, I don't have a calculator on me. Let me draw this arrow. So the acceleration of the rocket is going to be, let me whip out the handy dandy calculator. .7 divided by 0.114 minus 9.81. Our acceleration for a rocket is 31.42 meters per second squared. That is the acceleration of the rocket, and now since we have this value, we can plug it in to find the speed of the rocket at after the engine is done burning. So let's quickly jump over to that. So now we are going to be using our second equation, which is also in the PDF below, in the description. And it should be written as V is equal to V naught, that's what the little zero stands for, naught, plus acceleration multiplied by T. So a quick rundown of each of these letters. V stands for velocity, which is just another fancy way of saying speed. It is a little bit different than speed, but I don't want to get into that whole definition right now. So that's the speed, the end speed is equal to the starting speed, that's what naught means, 0 at time 0, plus the acceleration of the object, which we solved for in the previous part, multiplied by the time that object is accelerating, the time that the object is accelerating at that acceleration value. The acceleration value we have here is only when the engine is burning, because the engine doesn't burn for like the entire time of the flight. It starts and then stops, and then the rocket keeps going up a little bit until it slows down, and it slows down because of gravity, and after it falls back down again. So then we are only going to solve for the speed right when the engine shuts off, after it had been on. So our speed, V, is equal to our initial speed, our starting speed, which our starting speed was 0 meters per second, because the rocket wasn't moving at the beginning, it was on the launch pad still. So 0 meters per second, plus our acceleration of the rocket, which we found up here, 31.42 meters per second squared, multiplied by the time. So in this case, the time is the burn time, the time the engine is burning. And the engine burns for 1.9 seconds. So after doing a little bit of math, and I pulled the handy dandy calculator out again, we can find that 31.42 multiplied by 1.9 plus 0, the speed of the rocket is 59.698 meters per second. At the end as well, when we find our height, I'll make sure to put it in feet as well, because I know a lot of you guys watching don't really care about the meters part of this, because you guys think the imperial system is better, which personally I think the metric system is better. But that is a whole debate for another time. So we have our speed of the rocket right when the engine shuts off. now we are going to solve for at what height is the rocket at? How high in the sky is the rocket at when the engine shuts off? So we will now be erasing the board again and bringing in our second to last equation. There's only one more after this equation, and we will be solving for its height when the engine turns off. Okay, so our second to last equation, which is again listed in the PDF below, it should be on the second page like the other ones in the left-hand column, at the top of the left-hand column. So the equation should be this: x is equal to x naught plus v naught multiplied by t plus, I'm sorry if my pluses look like t's, plus 1/2 or half of the acceleration multiplied by the time, and the time is squared. So the good thing here is a lot of these things are going to be 0 because our rocket, I should actually explain the letters first. So x is the height of the rocket. In this case, like I said before, we're finding the height of the rocket when the engine turns off. X naught, like V naught, is the beginning height. The rocket starts on the ground, so we're going to call that height 0. So that will be 0. X is equal to 0. Plus V of naught, like in the previous equation, V of naught, the rocket starts off on the launch pad not moving. So it's also 0. And anything, and even if the time, the burn time, like we did last time, anything times 0 is 0. So we're just going to keep it like that. It'll be 0 meters. I should probably put units. Plus, that's fine. We don't need units. Screw the units. 0 plus 1/2, again, our acceleration of the rocket, 31.42 meters per second squared, multiplied by the time, and this is again, like in the previous equation, the time that this acceleration is true, is the actual value. So 1.9 seconds squared, because that's the burn time. That's the time that the engine is burning, and this is the acceleration only when the engine is burning. So now, like I said, we have a bunch of zeros, so these two things are canceled out, and it's really just this chunk of math that we will be doing. So we're going to pull out that handy dandy calculator again, and we are going to multiply 1.9 squared, so 1.9 times 1.9, multiplied by 31.42, which, and then multiply that again by 1/2, or 0.5. So our rocket, when the engine turns off, is going to be 56.71 meters in the air, which sounds about right compared to other rockets, other model rockets. Of course, not like Starship or Artemis or anything, or the Apollo or anything like that. So yeah. Now, since we have that, we have one last equation, and this equation is when we're going to add up everything we've been doing from the previous equations, and we are going to find the final height of our rocket. Okay, so our last equation, that is also again on the PDF attached below. It should be written as v squared is equal to v naught squared plus 2ax. Or it might be delta x, which delta is just a symbol for is a triangle, which is the triangle. Delta is a Greek alphabet letter, a Greek letter. Or it might be written as x minus x naught. So, like we've seen before, v is the speed, v naught is the beginning speed, 2 is just the number 2, a is the acceleration of the rocket, multiplied by x, which is the final height, minus x naught, which is x naught is the beginning height. But now our rocket doesn't have, the engine is turned off, like the engine has no more fuel, it's all burnt out. So there is no more thrust. So our acceleration, if we do it again, the sum of the forces now is just force of gravity, because the force of thrust, the engine isn't burning, so the force of thrust is gone. So it's only force of gravity. And because it's in the negative direction, the force of gravity is going to be negative. As we said before, the sum of the forces is equal to mass times acceleration, and as well as we can substitute that in for the force of gravity, which is equal to negative mass times the acceleration of gravity. Now, mass of the rocket, acceleration of rocket, mass of rocket. We divide each side by mass of rocket, and we're given acceleration of the rocket is equal to negative g, or the acceleration of gravity. So now our rocket is decelerating, it's accelerating in the negative direction, so it's slowing down. So this is going to be our new acceleration that we'll be plugging into this equation. You can sort of split up the launch into 3 different parts. The launch to when the engine burns out and is done burning, that's chunk 1, which is what we did at the beginning, which is what we just finished. Now we're on to chunk 2, which is when it's slowing down and it's going to reach its total height before falling down. And then chunk 3 is when it's falling down, and hopefully the parachute should deploy. So now we will be substituting again, like I said, the acceleration in for there, and let's get it. So we will have another substitution. Another one of these speeds is going to be 0. V is the final speed. V naught is the beginning speed. Our final speed for this rocket, like I said, the chunk 2 begins when the engine is done burning, and it ends when the rocket is at its final height, and it's technically not moving. So technically its final speed is 0, because for a split instant at the top of its path, at the top of its flight, it won't be moving. But it's such a small amount, like small sliver of time, that it almost looks like it's never not moving. So, but it's still 0, because that is its top of its height. Which is equal to our beginning speed, and this is the beginning speed of chunk 2, which is the final speed of chunk 1. So, like we solved for earlier in our our second problem, where we're solving for the speed of the rocket when the engine is done burning. And so it's 59.698 meters per second squared plus 2. The acceleration is negative g, so negative 9.81 meters per second squared. I'm going to have to erase some of this. And then our x final, or x, just x, is our final height minus the initial height. Again, sort of like the initial velocity, or the beginning speed, our beginning height is the final height of chunk 1. The beginning height of chunk 2 is the final height of chunk 1. So that is the height we just solved for in the previous part, 56.71 meters. Now, by doing some algebra, we will subtract, so we'll square this using the PEMDAS rules. We'll square this as well doing parentheses, don't forget parentheses, because technically that's first. We are going to multiply those things, these two things, for parentheses, and then we will square this and subtract it to this side. So, let's do step by step then. So, 59, pulling out the handy dandy calculator again. 59.698 times 59.698 is 3,563. And we're going to be subtracting it because we need to bring it to that side, because we want x to be all by itself. So negative, because we're subtracting it from both sides, negative 3,563.85 meters squared per second squared is equal to 2 times negative 9.81, which we're doing this part, which is equal to 19.62 times x minus 56.71 meters. Then we divide each side by 19.62. So negative 3,563.85 divided by 19.62 gives us 181.64 meter. This is meters per second squared, so that will give us meters, is equal to x minus 56.71 meters. Now we add 56.71 to each side, and that means our rocket will travel about, because we didn't calculate air resistance, about 181.64 plus 56.71, 238.35 meters, approximately, because we didn't calculate, we didn't consider air resistance. And that is the math done. So now I will explain my little handy dandy homemade tool to prove the height of the rocket, and we will go launch this rocket. This is my tool. It's made out of cardboard, toothpicks, a little bit of hot glue, and some tape to keep it tethered together. And I may have stolen this design from Estes themselves, but it is much cheaper than the $12 item they're trying to sell made out of plastic. Because I made this at home in about 10 minutes. So how does it work? So you may not be able to see, but I'll draw a more detailed version here. I'm gonna draw like this. kind of looks like a flashlight, and then it's got a little dangly thing. Like that. Along the cardboard semicircle, half circle, are a bunch of degree lines to measure the angle. So, at launch, the launch pad's here. I will be some distance away from the launch pad, and I'll have one of my helpful little minions launch the rocket for me. And I will be measuring. I will always have this center, this little toothpick here, aligned with the middle of the rocket. And then after it launches, as it goes up, I'll angle it more and more. But because of this heavy weighted part with the hot glue, it'll stay hanging down, and it will give me an angle that I'm pointing up. So let's say the angle is about 60 degrees. That's how high it ends up going. I don't have much room on the whiteboard, so it's definitely not 60 degrees, but let's just say it is. We're going to use some simple geometry, specifically sine, cosine, and tangent. And then let's say that we are 100 meters away. 100 meters away from the launch pad. And we get an angle of 60 degrees when the parachute deploys. This is just hypothetical. We know that SOHCAHTOA, tangent of the angle is equal to the opposite divided by the adjacent. So tangent of 60 is equal to the opposite, the height, divided by the adjacent, which is how far away I am from the launch pad, which is 100 meters. And this is assuming the rocket goes straight up, which it most likely won't because wind is a thing, sadly. So tangent of 60 is sine over cosine of 60, and sine of 60 is square root of 3 over 2. So tangent of 60 is the square root of 3 multiplied by 100 meters is equal to x, because we are bringing the 100 meters all by multiplying each side by 100 meters, so we can get x all by itself. And tangent of 60 is equal to square root of 3. So, bringing out the handy dandy calculator again. Square root of 3 multiplied by 100 gives us a height of 173.2 meters, which is actually probably around what the rocket will go up to, because again, we didn't consider air resistance when we were solving it, and this is, in real life, there will be air resistance, so technically it's going to be less than what we calculated. So it's probably going to go, if I'm 100 meters away from the launch pad, which I will not be because that's very far, it should go about 60 degrees, maybe a little bit higher. Really? I think it's going to go just around 60 degrees. So, and then as the closer you go to the launch pad, the higher the angle is, and the further away you go, the smaller the angle will be. But the math will still come out in the same way. So, that is my little homemade contraption, and let's go launch a rocket.
They ask you how you are, you just have to say that you're fine when you're not really fine, but you just can't get into it because they would never understand.
So, you know how I said earlier when we had to be away a certain distance from the launch pad? And we are assuming the rocket goes straight up. Well, it didn't really go straight up. it sort of went, it went higher, but you get the idea. It started in front of me and went behind me. So my angle is going to be greater than 90 degrees, which it should have been from 0 to 90. It could have also, the main reason why it did that is because I was too close to the launch pad. I was about 100 feet away with according to the measuring tape. And in the example that I said earlier, we're 100 meters away, which is about 300 feet. If I was 300 feet away from the launch pad, I definitely would have been able to have the landing in front of me. I mean, as well, like the entire thing was pretty much a failure. Starting with the very first rocket I did, where the engine, we had a messed up engine and it went light. So well, we yeah, the angle I measured, because I sort of turned as it went, was I measured 60 degrees, and I think the math came out to about 58 meters high, and the math, according to the tool I made, it was 58 meters high, and we measured 238 meters, and the box says the rocket goes 183 meters, and the box is accounting for air resistance. So it was a fail, but you know what? We learn more from failures than we do from successes, and we're gonna take this and we're gonna try it again, but not so soon because I have some few plans for the next video. But yeah, that's it for next video. So for this video, but yeah, next video we're building rocket fuel. We're gonna stick into a PVC pipe, and then we're just gonna light it and see which one has the most thrust, and we're gonna try to find a good ratio of fuel to ingredients and stuff. And yeah, that's it. Thank you very much for watching, and sorry for the disaster as well as the parachute not deploying, and especially the long wait for the video. But I plan on getting the next video out as soon as I can. I'm expecting it within 1 to 2 weeks. But yes, thank you for watching.